One moment, the ground beneath you is perfectly still, solid, unshaken, dependable. The next, without warning, the earth itself seems to rebel. Buildings rattle, roads crack, and the terrifying realization hits. There was no foreshadowing, no known fault line nearby, nothing to suggest this was coming. This isn't science fiction. These are ghost faults, earthquakes that strike like phantoms, leaving destruction in their wake, and scientists scrambling for answers. How can the Earth move so violently in places where it shouldn't? What unseen forces are at work beneath our feet? And perhaps most unsettling of all, could one of these mysterious tremors happen where you live? For centuries, these unexplained quakes have haunted human history. Ancient cultures blamed gods or monsters, weaving myths to explain the ground's sudden fury. Today, we know the Earth's crust is far more complex than we once thought, riddled with hidden fractures and stresses that defy our maps. But ghost faults aren't just geological oddities, they're urgent mysteries with real consequences. Cities built in seemingly stable regions have been caught off guard by tremors no one predicted, proving that our understanding of the planet is still incomplete. This is the story of science's greatest geological detective work. We'll journey from forgotten archives to high-tech labs, where researchers piece together clues like forensic scientists at a crime scene. You'll discover how satellites peer deep into the Earth's hidden layers, how centuries-old earthquake records hold startling new insights, and why cracking the code of ghost faults could rewrite what we know about seismic risk. The ground beneath us holds secrets, and the more we uncover, the better we can protect ourselves from the next invisible threat. So let's dig in, because the truth is down there, waiting to be found. Imagine the Earth's crust as a giant jigsaw puzzle, except some of the pieces aren't just moving, they're hiding. Traditional fault lines where tectonic plates grind against each other are like the puzzle's obvious seams. But ghost faults, they're the invisible cracks, the ones that don't show up on any map until the ground suddenly shifts beneath us. Scientists now believe these hidden fractures form when stress builds up in unexpected places, far from known plate boundaries. Over time, that pressure finds release in a violent snap, an earthquake that seems to come from nowhere. Detecting these phantom faults is like trying to spot a shadow in a dark room. Geologists rely on cutting-edge tools to uncover clues. LiDAR, for example, uses laser pulses to map the ground's surface in astonishing detail, revealing subtle warps or bulges that hint at movement below. Satellites equipped with radar can measure millimeter-scale shifts in the Earth's crust over time, painting a picture of silent strain accumulating where no one thought to look. Even seismic waves from distant earthquakes can act like X-rays, exposing weaknesses in the rock that traditional surveys miss. The stakes couldn't be higher. Cities like Prague, which sits far from any major fault line, have experienced damaging quakes traced back to these hidden fractures. And in the central United States, where the ground was once thought to be stable, a surge in seismic activity has been linked to ancient faults reactivating under new pressures. The unsettling truth is that our planet's crust is far more dynamic and unpredictable than we ever imagined. But with every ghost fault uncovered, we gain a chance to rewrite the rules of earthquake preparedness, turning blind spots into guarded territory before the Earth moves again. Centuries before satellites or seismographs, people across the world documented earthquakes that defied explanation. In the year 763, monks in an English monastery scribbled a chilling note in their chronicles. The Earth shook violently where no such thing was ever known before. Half a world away, Native American oral traditions from the Mississippi Valley describe sudden tremors that split the ground open, far from any mountain ranges or coastal zones where quakes were expected. These weren't isolated incidents. From the cobblestone streets of Prague to the farmlands of Missouri, historical records are filled with reports of the ground moving where it supposedly couldn't. What makes these accounts so compelling isn't just their age, it's their eerie consistency with modern ghost fault discoveries. Take the New Madrid earthquakes of 1811 and 1812, a series of massive quakes that rang church bells in Boston and reversed the flow of the Mississippi River. At the time, scientists dismissed the region as seismically inert. Today, we know it sits atop a network of ancient, buried faults that occasionally reawaken. Similarly, medieval European texts describing the earth groaning where no mountains stand now align with LiDAR scans revealing hidden fractures beneath those very regions. The real breakthrough comes when we treat these historical accounts not as folklore but as data points. By cross-referencing ancient earthquake descriptions with modern geological surveys, researchers have identified patterns. Areas that experienced mysterious tremors centuries ago often show subtle ground deformations today, tiny wrinkles in the landscape that hint at slow, invisible movement below. Even more telling, many of these quiet zones are now known to sit above geological weak spots where continental plates, though far apart, still transfer stress through the rigid crust like cracks spreading through frozen ice. Perhaps the most haunting lesson from these old records is their reminder of how quickly we forget. Communities rebuilt after unexplained quakes, their warnings fading into local legends until the next generation was caught unprepared. Today, as we uncover ghost faults beneath modern cities, those historical tremors take on new urgency, not as curiosities, but as mile markers on a much longer timeline of the Earth's hidden restlessness. The past is whispering where the next phantom quake might strike. The question is whether we're listening. The New Madrid earthquakes of 1811 and 1812 weren't just powerful, they rewrote the rules of what we thought possible. In the dead of winter, while most of North America slept, the Mississippi Valley became a seismic war zone. The first massive quake struck just after 2 in the morning on December 16, 1811. Its force so tremendous that it knocked people off their feet as far away as Chicago. But the real shock came when witnesses saw the impossible, the Mississippi River flowing backward. For hours, the river ran in reverse as the quake's energy warped its channel, creating temporary waterfalls and swallowing islands whole. What made these quakes so extraordinary wasn't just their violence, it was their location. This wasn't California or Japan, where earthquakes were expected. The Mississippi Valley sat hundreds of miles from the nearest tectonic plate boundary, in what geologists then considered a geologic safe zone. Yet over 3 months, the region endured at least 3 quakes estimated at magnitude 7 or higher, plus thousands of aftershocks. Church bells rang in Boston from the vibrations. President James Madison felt tremors in the White House. And in the epicentral zone, the ground moved like liquid, with sand volcanoes erupting in fields and cracks splitting the earth wide enough to swallow trees. Modern research paints an even more startling picture. Deep beneath the Mississippi Valley lies a network of ancient faults, remnants of a failed continental rift from 500 million years ago. Unlike California's famous San Andreas Fault, these cracks don't show clearly at the surface. They're hidden under layers of sediment, dormant for centuries until stress builds to a breaking point. Some scientists now believe the New Madrid zone acts like a seismic battery, slowly storing energy from the gradual movement of the North American plate until it discharges in catastrophic bursts. Others point to mysterious hotspots in the mantle that might weaken the crust from below. The controversy isn't just academic. If hidden faults caused the New Madrid disasters, similar zones could lurk under other, stable regions. Recent satellite data shows the ground around Memphis directly above the fault system still shifts about 5 millimeters per year, proof that the Earth here never truly settled. Meanwhile, paleoseismologists digging along the Mississippi have uncovered evidence of even older megaquakes from 1450 and 900, suggesting a terrifying pattern. Every few centuries, without warning, this quiet farmland transforms into one of the most dangerous seismic zones on the continent. What keeps researchers awake at night isn't just the past, it's the future. Today, millions live in cities like St. Louis and Memphis that didn't exist in 1811. Skyscrapers, bridges, and pipelines now sit atop the same ground that once liquefied. A repeat of the New Madrid quakes could devastate the American heartland in ways we're only beginning to prepare for. Yet perhaps the most humbling lesson is this. If the Earth could hide such destructive power beneath the Mississippi Valley's peaceful surface, where else might ghost faults be lurking, silent and unseen, waiting for their moment to shake the world? To understand why ghost faults keep scientists up at night, we need to compare them to their more predictable cousins, the traditional faults we've mapped for decades. Picture the San Andreas Fault in California, a visible scar running through the landscape where two tectonic plates grind past each other like gears stuck in slow motion. Earthquakes here follow recognizable patterns, allowing engineers to design buildings that can sway with the shaking. But ghost faults, they're the ultimate geological wildcards, hidden fractures that don't play by the rules. The key difference lies beneath the surface. Traditional faults announce themselves with clear surface features, offset streams, linear valleys, or scarps where the ground has visibly shifted. Ghost faults, by contrast, are masters of disguise. Buried under layers of sediment or disguised by erosion, they leave no outward clues until the moment they rupture. Imagine a pane of glass with a hairline crack you can't see until one day, without warning, it shatters under pressure. That's the terrifying unpredictability of these hidden fractures. Timing is another critical distinction. Active faults like the San Andreas release stress in relatively frequent, smaller quakes, like a pressure valve gently hissing. Ghost faults, however, often stay silent for centuries or even millennia, building up strain like a coiled spring. When they finally snap, the energy release can be catastrophic. In 2008, a previously unknown fault beneath the Sichuan province in China unleashed a magnitude 7.9 earthquake that killed nearly 90,000 people. The region had no recorded history of major quakes, no reason to suspect the ground could turn deadly. What makes ghost faults particularly dangerous isn't just their invisibility, it's where they tend to hide. While traditional faults cluster near plate boundaries, ghost faults lurk in continental interiors, beneath cities that never planned for earthquakes. Buildings in these areas often lack seismic reinforcements, and residents rarely practice earthquake drills. When the New Madrid fault awoke in 1811, log cabins simply collapsed. Today, a similar quake would strike modern infrastructure, highways, pipelines, nuclear plants, all built without accounting for seismic risk. Scientists now suspect ghost faults may be more common than we ever imagined. Advanced imaging techniques reveal networks of buried fractures crisscrossing supposedly stable regions. Some appear to be ancient faults reactivated by new stresses, like old wounds reopening under pressure. Others form when the weight of glaciers or reservoirs bends the crust, creating fresh weaknesses. Even human activities like fracking or deep mining can awaken sleeping faults by altering subsurface pressures. The unsettling truth is that our planet's crust may be far more fractured and far less predictable than our maps suggest. This isn't just geology, it's a race against time. Every newly discovered ghost fault forces us to reconsider what earthquake country really means. Cities from Boston to Bangalore now face uncomfortable questions about their seismic vulnerability. The challenge isn't just finding these hidden dangers, it's convincing communities to prepare for a threat they've never seen. Because when a fault leaves no trace, the only warning may be the ground itself turning against us. The hunt for ghost faults has entered a new era, powered by technologies that would seem like science fiction just a generation ago. Seismic tomography, for instance, works like a CT scan for the planet, using waves from distant earthquakes to create three-dimensional maps of the Earth's interior. These images reveal subtle density variations in the rock, exposing hidden faults that traditional surveys miss. It's as if we've been given X-ray vision, allowing us to spot fractures buried dozens of miles beneath cities and farmland. Even more remarkable is the precision of modern GPS arrays. Networks of ground stations now track movements as tiny as the width of a pencil lead across entire continents. By measuring how these points shift over years, scientists can detect the slow creep of tectonic stress, even in regions where no fault lines appear on maps. In Oklahoma, for example, this technology helped identify previously unknown faults linked to a surge of earthquakes, proving that human activity like wastewater injection can awaken long-dormant fractures. Machine learning adds another powerful tool to the search. Algorithms trained on decades of seismic data can spot patterns invisible to human analysts, flagging subtle tremors that might signal a growing ghost fault. Researchers at Stanford recently used this approach to uncover a hidden fault beneath the Santa Cruz Mountains in California, a fault that had escaped detection despite decades of intensive study in one of the world's most seismically monitored regions. Perhaps the most surprising detective work happens from space. Satellites equipped with InSAR radar measure ground deformation with millimeter precision, creating color-coded maps that show where the Earth's crust is quietly buckling under strain. When a series of mysterious tremors shook Indonesia's Lombok Island in 2018, these satellite images revealed a previously unknown fault system, one that had been invisibly accumulating stress for centuries before its sudden, deadly release. What ties these technologies together isn't just their sophistication, it's their ability to connect dots across time. Paleoseismology, the study of ancient earthquakes, now collaborates with real-time data. By digging trenches across suspected ghost faults, scientists can uncover layers of sediment disturbed by past quakes, creating timelines that stretch back thousands of years. Combined with modern monitoring, this forms a dual lens, one eye on the deep past, the other on the present, both searching for warnings of what's to come. Yet for all these advances, ghost faults remain elusive. Many reveal themselves only in the seconds before rupture, when sensitive instruments catch the first telltale tremors of a fault beginning to slip. Others leave behind only cryptic clues, like the mysterious seismic waves that rippled around the globe in November 2018, originating from an unexplained event near Mayotte Island in the Indian Ocean. To this day, no one knows exactly what caused them, though some suspect the birth of a new underwater fault. The sobering reality is that we're still playing catch-up with our planet's hidden geology. Every new ghost fault discovered raises questions about others we haven't found yet. But with each technological leap, we chip away at the Earth's secrets, turning what was once invisible into something we can anticipate and perhaps one day predict. The ground may keep its secrets well, but science is learning to listen more closely than ever before. On August 23, 2011, at 1:51 in the afternoon, the east coast of the United States got a wake-up call it never expected. Office workers in Washington, D.C. felt their desks lurch violently as ceiling tiles rained down. The Washington Monument cracked like a porcelain vase. In New York City, 700 kilometers away, people streamed out of high rises as buildings swayed unnervingly. Even the Pentagon evacuated the culprit. A magnitude 5.8 earthquake centered near Mineral, Virginia, a region with no known fault lines and no history of significant seismic activity. This wasn't supposed to happen. Conventional wisdom held that earthquakes of this size only struck near plate boundaries, like California's San Andreas Fault or Japan's Pacific Rim. Virginia sat snugly in the middle of the North American plate, far from any tectonic drama. Yet for 90 terrifying seconds, the ground behaved as if it had forgotten its own rules. The quake caused over $200 million in damage, cracked the National Cathedral's spires, and even triggered the automatic shutdown of 2 nuclear reactors at the North Anna Power Station. The real shock came after the shaking stopped. When geologists rushed to study the epicenter, they found no visible fault line, just rolling farmland and dense forests. It was as if the earthquake had left no fingerprints, but beneath that peaceful surface, advanced imaging techniques eventually revealed the hidden culprit, a previously unmapped fault buried under half a kilometer of ancient sediment. This ghost fault, now called the Quail Fault, had been dormant for millions of years until stresses within the continental plate finally forced it to slip. What made the Virginia quake so scientifically significant wasn't just its surprise appearance. It was what it revealed about how continents behave. Unlike the clean breaks of boundary faults, intraplate quakes like this one often stem from ancient weaknesses in the crust. The East Coast, it turns out, is littered with fossil fractures from when North America was stitched together from smaller landmasses hundreds of millions of years ago. These old scars, long assumed to be geologically dead, can reawaken when modern stresses find them like a long-forgotten crack in a sidewalk, suddenly giving way under fresh pressure. The Virginia earthquake also exposed a troubling gap in preparedness. Building codes along the East Coast, designed with hurricanes in mind, offered little protection against seismic shaking. Historic landmarks suffered heavy damage precisely because no one thought to earthquake-proof them. Perhaps most alarmingly, the quake's effects spread much farther than expected due to the unique geology of the eastern U.S. The older, colder crust there transmits seismic energy more efficiently than the fractured rocks of California, meaning a moderate quake can shake an area 20 times larger than a similar event out west. In the years since, scientists have uncovered more ghost faults lurking beneath the Appalachians and coastal plains. Some appear linked to the same ancient tectonic collisions that built the mountain range 300 million years ago. Others may trace back to the stretching and rifting that occurred as the Atlantic Ocean first opened. Each discovery forces a re-evaluation of what we consider stable ground. Because if a fault no one knew existed could shake the nation's capital, what other seismic surprises might be hiding in the Earth's basement, waiting for their moment to remind us of their presence? The lesson from Virginia isn't just about one unexpected quake, it's about humility. Our planet's crust keeps secrets that defy surface appearances, and as we continue to uncover these hidden fractures, we're left with an unsettling realization. The ground beneath our feet may be far more unpredictable than our maps suggest. The only certainty is that earthquakes don't care what we know or don't know about where they're supposed to happen. Most earthquakes play by familiar rules. They announce themselves along the edges of tectonic plates, where continents collide or grind past each other in predictable patterns. But ghost faults specialize in breaking those rules. triggering what scientists call intraplate earthquakes. These seismic events strike like uninvited guests in the quietest neighborhoods of our planet, the stable interiors of tectonic plates where the ground isn't supposed to move. And when they do, the results can be catastrophic precisely because no one sees them coming. Take the case of Bhuj, India. In 2001, a magnitude 7.7 earthquake ripped through the Gujarat region, killing nearly 20,000 people. The devastation was magnified by sheer disbelief. This wasn't the Himalayan fault zone to the north, but the supposedly stable Indian peninsula. Investigations revealed the quake originated from a buried fault that hadn't moved in over 9,000 years. Like a dormant volcano suddenly erupting, this ghost fault reminded us that geological silence doesn't mean safety. What makes intraplate quakes so dangerous lies in their physics. At plate boundaries, frequent smaller quakes release stress like controlled burns preventing wildfires. But within plates, stress accumulates unchecked for millennia, building to catastrophic releases. It's the difference between a balloon slowly leaking air and one that pops without warning. When these hidden faults finally rupture, they often produce sharper, more concentrated shaking because the older, colder rock transmits seismic energy more efficiently. That's why the 1886 Charleston earthquake, a magnitude 7 that struck South Carolina's intraplate zone, toppled buildings as far away as Chicago and rattled church bells in Boston. Scientists now recognize these events aren't flukes but part of a global pattern. Beneath every continent lie ancient scars, failed rifts from when continents tried to split apart, collision zones from when supercontinents formed, or weak spots from when the crust first cooled. These features might as well be invisible until modern stresses reactivate them. In Australia, miners digging near Newcastle in 1989 accidentally tapped into one such weakness, triggering a magnitude 5.6 quake that killed 13 people in a region with no recorded seismic history. The emerging understanding of intraplate quakes forces us to rethink earthquake preparedness worldwide. Cities like Boston and Paris now conduct seismic hazard assessments that would have seemed absurd 50 years ago. Engineers in the Midwestern United States, once considered seismically inert, are retrofitting bridges to withstand shaking after discovering active faults beneath the Mississippi embayment. Even more unsettling are the zones we haven't fully investigated yet, like the Amazon basin or the Siberian platform, where geological surveys remain sparse but ghost faults could lurk. Perhaps the most humbling lesson comes from studying how continents heal. Some intraplate faults, like wounds that never fully close, remain weak points for billions of years. The New Madrid seismic zone, for instance, follows a failed rift that formed when Rodinia, a supercontinent predating Pangaea, began breaking apart over 700 million years ago. That ancient weakness still occasionally trembles, proving that the Earth's memory far outlasts human history. Our challenge isn't just mapping these ghostly fractures, it's learning to respect the hidden vulnerabilities of ground we once called stable. Because when the rules of seismology get rewritten, the consequences are measured in lives, not textbooks. Long before seismographs or tectonic theory, ancient cultures wove dramatic explanations for the Earth's sudden violence. In Japan, the colossal catfish Namezu thrashed beneath the islands, its movements causing quakes until the god Kashima pinned it down with a stone. Native tribes along the Pacific Northwest spoke of thunderbird battles with whale, their struggles shaking the ground. Greek myths told of Poseidon striking the earth with his trident when angered, while Hindu texts described 8 massive elephants supporting the world when one tired, the planet trembled. These vivid stories share an uncanny thread. They often emerged in regions now known to sit atop ghost faults. What if these myths weren't just imaginative tales, but ancestral warnings encoded in folklore? Consider the Maori legend of Uamoko, the god of earthquakes, said to stir within New Zealand's geothermal regions. Modern mapping reveals these areas are laced with hidden faults where the Pacific and Australian plates grind together beneath thick sediment. Similarly, the Cherokee story of the great buzzard whose wings beat so hard they carved valleys and triggered tremors originated in the Tennessee River Valley, now recognized as part of the same seismic zone that includes the New Madrid fault system. The parallels are too striking to dismiss as coincidence. Archaeology lends credence to this connection. At Çatalhöyük in Turkey, one of the world's oldest cities, researchers found a 9,000-year-old mural depicting a volcanic eruption and collapsing buildings. The settlement sat near multiple fault lines, including some that remained hidden until recent LiDAR surveys. In the American Southwest, Puebloan structures show deliberate earthquake-resistant designs like flexible timber frameworks, suggesting ancient builders knew more about seismic risks than we assumed. These adaptations hint at hard-won knowledge passed down through generations, knowledge that may have originated with witnessing ghost fault activity. The most compelling evidence comes from dating myths to seismic events. The ancient Greek story of Atlantis sinking into the sea aligns with geological evidence of a massive tsunami around 1628 BCE, when the Santorini eruption triggered earthquakes along submerged faults. Aboriginal Australian tales describing the earth cracking open like an egg match paleoseismic records of quakes along the Darling Fault, which runs beneath the continent's western edge. When oral traditions from disparate cultures describe similar ground behaviors, liquefaction, landslides, or strange booming sounds in the same geologically active zones, it suggests these stories preserved real observations across millennia. What emerges is a radical rethinking of how ancient peoples understood their world. Without modern science, they mapped seismic hazards through storytelling, turning terrifying experiences into memorable narratives that could outlast written records. The details might be mythological, but the locations and effects often ring true. Today, researchers are compiling these legends into what they call folk seismology, treating them as alternative datasets that could point to overlooked fault lines. In China, where imperial earthquake records date back 3,000 years, historians and geologists collaborate to cross-reference ancient reports with modern seismic gaps, areas that suspiciously haven't quaked in recent memory. This interdisciplinary approach has already borne fruit. When geologists investigated a persistent Lakota legend about the time the Earth wept black tears near the Missouri River, they discovered evidence of prehistoric sand volcanoes, a telltale sign of liquefaction during powerful quakes. The site now helps track the recurrence interval of New Madrid system events. Similarly, Inuit accounts of mountains walking in Canada's Arctic led researchers to identify previously unknown faults along the Beaufort Sea coast. These successes raise an urgent question. How many other ghost faults might be hiding in plain sight, encrypted in stories we've dismissed as mere mythology? The wisdom of ancient cultures challenges our assumptions about seismic risk assessment. While we rely on instruments that measure decades of data, their traditions carried warnings across centuries. Perhaps it's time to listen, not just to the ground beneath us, but to the voices of those who felt its tremors long before our science could explain them. Because sometimes the clearest map to hidden dangers isn't drawn in lines, but in legends. The Earth's crust is far from the unshakable foundation we imagine. It's more like a vast, slow-motion battleground where invisible forces wage a silent war. Even in regions we've labeled stable, stress builds relentlessly as tectonic plates transmit pressure across thousands of kilometers like a game of geological telephone. Picture a wooden board being bent ever so slightly each year, seemingly solid, until one day it splinters along a hidden grain no one noticed. That's the reality of ghost faults: fractures we can't see, stress we rarely measure, and ruptures we seldom expect. What makes this hidden buildup of stress so treacherous is how it migrates. Unlike the steady creep along well-mapped faults, stress in stable continental interiors can travel unpredictably through the crust, funneling into weak zones formed eons ago. Deep beneath the surface, ancient rifts, failed continental splits from hundreds of millions of years ago, act like scars that never fully healed. These zones, though long dormant, remain the path of least resistance when modern forces push and pull the crust. Researchers now compare it to an old ceramic plate. Drop it, and it won't break along fresh lines but along the faint cracks from decades of use. Cutting-edge models reveal how stress finds these weak spots. Using supercomputers, scientists simulate the Earth's crust as a dynamic puzzle, mapping how stress redistributes after distant earthquakes or even the melting of ice sheets. One startling discovery: the weight of glaciers during the last ice age actually bent continental plates, and as those glaciers retreated, the rebounding crust triggered earthquakes along forgotten faults. Today, similar stresses might come from human activity: reservoirs filling with water, oil extraction altering subsurface pressures, or even the sheer weight of growing cities. The real challenge lies in detecting these silent shifts before they turn deadly. One promising method involves tracking slow slip events, tiny, days-long movements along faults that don't produce noticeable shaking but telegraph growing stress. In the Pacific Northwest, sensors have caught ghost faults whispering these warnings miles beneath the surface. Elsewhere, scientists monitor earthquake swarms, clusters of small tremors that might signal stress fluidly moving through hidden fracture networks. It's like listening for faint cracks in the walls of a house before the foundation gives way. Perhaps the most unsettling revelation is how quickly stress can localize. A fault might slumber peacefully for millennia, then due to a subtle change in pore pressure or a distant quake's ripple effects, transform into a seismic threat almost overnight. The 2017 Mexico City quake demonstrated this horrifyingly. Stress from the colliding Cocos Plate traveled hundreds of kilometers inland, rupturing a fault no one had prioritized. The result: buildings collapsed in a metropolis that had prepared for different seismic threats entirely. This isn't just academic, it's a race to redefine safety. Engineers once designed skyscrapers based on historic quake patterns. Now they must account for stresses that could target entirely new weak points. Cities from Dallas to Delhi are drilling deep boreholes to measure paleo pressure, the fossilized stress trapped in ancient rocks. Meanwhile, satellites map millimeter-scale ground deformations, hunting for telltale bulges where stress is concentrating. The deeper we look, the clearer it becomes. Stability is an illusion. The Earth's crust is a living archive of past collisions, rifts, and scars, all waiting to reactivate under the right conditions. And as we uncover more about how stress navigates this hidden labyrinth, one truth grows undeniable: the next ghost fault won't announce itself with fanfare. It'll strike where we least expect, armed with pressures we're only beginning to understand. Imagine standing on what feels like perfectly solid ground when suddenly, the earth beneath you begins whispering. Not with one violent jolt, but with dozens, sometimes hundreds of tiny tremors rippling through the crust over weeks or even months. These aren't aftershocks trailing a major quake. They're earthquake swarms, one of geology's most puzzling phenomena, where the ground seems to shudder in conversation with itself, leaving scientists scrambling to decode its cryptic language. Unlike typical quake sequences where a powerful main shock is followed by gradually diminishing aftershock swarms play by different rules, there's no starring actor, no clear starting point, just a chorus of small quakes that can persist relentlessly. Take the Yellowstone caldera, where swarms of up to 3,000 tremors have shaken the park in a single month, all clustered tightly in time and space, yet never culminating in a catastrophic rupture. Or the Cahuilla swarm in Southern California, which produced over 22,000 detectable quakes between 2016 and 2018, each one a faint tap on the Earth's door, asking a question we're still learning to answer: what's really moving down there? The connection to ghost faults is where the story gets fascinating. Many swarms trace back to hidden fractures where stress leaks out gradually rather than snapping catastrophically. Picture a zipper slowly coming undone instead of a rope snapping under tension. These creeping movements, technically called a seismic slip, transfer stress so subtly that traditional seismometers might miss the buildup until the swarm begins. In Iceland, researchers have watched swarms migrate along buried faults at glacial speeds, sometimes just meters per day, as pressurized fluids lubricate the rock, allowing it to slide almost silently. What makes swarms so valuable to science is their transparency. While big quakes obliterate the very faults they rupture, swarms leave behind a detailed record of stress migration. By mapping their progression, scientists can trace the invisible pathways of fluid or stress through the crust like following breadcrumbs. Near the Salton Sea in California, swarm quakes have illuminated a web of interconnected microfractures that act like geological plumbing, channeling heated water and redistributing strain. Each tiny tremor is a flashbulb moment, briefly illuminating the hidden architecture of the Earth. The real hope lies in what these patterns might reveal about larger quakes. Some studies suggest swarms could be the Earth's way of testing its own weaknesses, probing fracture networks until it finds the path of least resistance. In Japan's Noto Peninsula, a 2-year swarm preceded a magnitude 6.3 quake, hinting that these events might someday serve as early warnings. Other swarms, like those along the mid-Atlantic ridge, simply dissipate without fanfare, leaving no damage but priceless data about how stress diffuses through oceanic plates. Technology is now giving us eyes where we once had only theories. Fiber optic cables buried under cities, the same ones that deliver internet, can be repurposed as ultra-sensitive seismic arrays, detecting swarm quakes too faint for traditional networks. Machine learning algorithms sift through decades of swarm data, hunting for hidden precursors that might predict larger ruptures. And in labs worldwide, geologists simulate swarm conditions with blocks of rock and pressurized fluids, watching how microscopic fractures evolve under stress. Yet for all our progress, swarms remain stubbornly enigmatic. Some, like those near the San Andreas Fault, appear to relieve stress harmlessly. Others, like the Prog swarm in Oklahoma, escalated unexpectedly into damaging quakes linked to wastewater injection. The terrifying truth is that we're still learning the rules of this geological murmuration, and until we do, every swarm represents both a tantalizing clue and a potential prelude. One thing is certain: the Earth speaks more softly than we realized, and if we want to understand its warnings, we'll need to listen closely to even its quietest tremors. Cities expanding over forgotten fault lines are like houses built on invisible cracks. Everything seems fine until the ground remembers its secrets. The 1994 Northridge earthquake in California was a wake-up call, not just for its 6.7 magnitude tremors, but for how it revealed a fault no one had mapped. This hidden fracture lurked beneath suburban sprawl, its rupture damaging thousands of buildings and claiming dozens of lives. What made Northridge so shocking wasn't just its strength. It was the realization that even in one of the world's most seismically studied regions, ghost faults could still ambush modern cities. Urban development has a way of silencing the Earth's warnings. asphalt and concrete blanket the landscape, hiding subtle ground deformations that might hint at buried faults. High rises add immense weight, altering subsurface pressures in ways we're only beginning to understand. In Tokyo, where skyscrapers cluster atop the Kanto Plain, engineers discovered that building vibrations can actually mask the faint seismic signals of accumulating stress, like trying to hear a whisper in a thunderstorm. Meanwhile, underground projects, subway tunnels, parking garages, utility corridors, can inadvertently intersect hidden fractures, acting like pins poking at a balloon. The stakes are highest where complacency runs deep. Consider Seattle, where the 1909 Alaska Yukon earthquake sent tremors strong enough to crack sidewalks, yet a century later, many buildings still weren't retrofitted for seismic threats. Then in 2001, the Nisqually quake struck, originating from a deep ghost fault no urban planner had prioritized. The damage reached $2 billion, much of it concentrated in structures deemed low risk. Similar stories unfold worldwide. In Christchurch, New Zealand, where a 2011 quake ruptured a previously unknown fault under the city center, or in Tainan, Taiwan, where a 2016 tremor exposed weaknesses in high rises built over sedimentary basins that amplified shaking. Engineers are fighting back with ingenious adaptations. In Los Angeles, new high-rises use base isolation systems, essentially giant shock absorbers that let buildings sway independently of the ground. Tokyo's skyscrapers incorporate tuned mass dampers, massive pendulums that counteract seismic motion, but the real innovation lies beneath the surface. Advanced ground-penetrating radar now scouts construction sites for hidden fractures, while AI analyzes decades of satellite data to spot millimeter-scale ground shifts that might betray a ghost fault's presence. Some cities are even experimenting with seismic invisibility cloaks, concentric rings of underground barriers designed to deflect earthquake waves away from critical infrastructure. The lessons from these disasters have rewritten urban planning playbooks. Modern seismic codes now account for something called liquefaction zones, areas where sandy soil can turn to quakes and during shaking. In the Bay Area, maps of these zones look like Swiss cheese, with neighborhoods built atop old creek beds or landfill at far greater risk. Engineers also focus on soft-story buildings, structures with weak ground floors like parking garages, which collapsed catastrophically in both Northridge and Turkey's 2023 quakes. Retrofitting these vulnerable spots has become a priority from Lisbon to Jakarta. Perhaps the most profound shift is in how we define risk itself. Traditional hazard maps relied on historical quake records, but ghost faults operate on timelines longer than human memory. New probabilistic models incorporate paleoseismic data, factoring in quakes that occurred thousands of years ago. The results are sobering. Boston's skyscraper district, once considered seismically inert, now shows a 1 in 20 chance of experiencing damaging shaking within 50 years due to ancient faults beneath the Massachusetts coast. Similar reassessments are underway for Madrid, Nairobi, and other cities far from plate boundaries. The challenge isn't just technical, it's psychological. Convincing communities to invest in earthquake preparedness for threats they've never seen requires overcoming what risk experts call the disaster imagination gap. After the Nepal quakes of 2015, researchers found that villages with oral histories of past tremors had preserved traditional earthquake-resistant building techniques, while others had abandoned them over generations. Today's urban planners face a parallel dilemma: how to make invisible risks feel urgent enough to act upon. As cities continue expanding, the dialogue between human ambition and geological reality grows more complex. Each new ghost fault discovery forces a reckoning not just with the limits of our knowledge, but with our relationship to the ground we build upon. The Earth keeps its secrets well, but it also leaves clues for those willing to look closely enough. In the end, resilient cities aren't those that never shake, but those that learn to bend without breaking when the hidden fractures finally stir. The debate over ghost fault origins splits geology into two fascinating camps, each armed with compelling evidence. On one side, researchers point to the Earth's long memory, the idea that ancient tectonic battles leave behind scars that never fully heal. Picture a ceramic plate dropped centuries ago. Even if repaired, the faintest hairline cracks remain, vulnerable to future stress. This camp argues that ghost faults are geological ghosts in the truest sense, relics of continental collisions, failed rifts, or vanished oceans from hundreds of millions of years ago. When modern forces like plate movement or glacial rebound reactivate these fossilized weaknesses, the result is an earthquake that appears to come from nowhere, but actually taps into the planet's deepest history. Support for this theory comes from surprising places. In the American Midwest, seismic surveys reveal faults aligned with a billion-year-old rift system that nearly split North America apart before mysteriously stalling. Similarly, earthquakes in Australia's outback trace back to fractures formed during the assembly of the supercontinent Gondwana. Even more telling are laboratory experiments where scientists compress rock samples containing artificial, fossil fractures. The old cracks consistently reawaken under stress, while new ones form less easily. It's as if the crust has a preference for reopening old wounds. Yet another group of scientists champions a radically different view, that ghost faults are born from modern stress realignments, emerging fresh in response to today's tectonic forces. They compare the crust to a pane of glass being twisted slowly. New cracks can form anywhere the strain becomes intolerable, not just along pre-existing flaws. This camp highlights regions like Oklahoma, where wastewater injection has triggered quakes along previously inactive faults, proving that human activity can create seismic threats where none existed. Similarly, the removal of glacial ice after the last ice age caused parts of Scandinavia to rebound, generating new fractures in crust that had been stable for millennia. Satellite data adds fuel to this theory. Advanced InSAR radar maps show continental interiors deforming in ways that don't align with known ancient structures. In Central Asia, for example, GPS measurements reveal the Indian plate pushing northward like a bulldozer, crumpling the Tibetan plateau and spawning fresh faults far from the main collision zone. These modern fractures behave differently than ancient ones. They're often shorter, more chaotic, and harder to predict, like cracks spreading through drying mud rather than along predetermined lines. The most intriguing cases blur the lines between these theories entirely. Take the New Madrid seismic zone. Its faults follow an ancient rift, but the quakes there may also be fueled by dense remnants of oceanic crust sinking into the mantle below, a process that started relatively recently in geological terms. Or consider the 2011 Virginia earthquake, which occurred near a suture zone where continents merged 300 million years ago, but was likely triggered by present-day stress transmitted across the North American plate. These hybrid scenarios suggest that ghost faults might be both old and new, simultaneously ancient weaknesses exploited by modern forces. What unites both theories is their shared revelation about our planet's restlessness. Whether fossilized or freshly minted, ghost faults remind us that the Earth's crust is never truly at rest. It's a dynamic mosaic of stress, memory, and adaptation. Every newly discovered fault, whether whispering with ancient echoes or cracking under contemporary strain, forces us to redraw our maps of seismic risk. Because the ground doesn't care which theory we prefer, it moves according to its own hidden logic, leaving us to piece together the clues after the shaking stops. Most earthquakes play by the rules, rattling the upper layers of the Earth's crust where rock behaves like brittle glass, cracking under stress. But ghost faults have a habit of breaking conventions, including depth. While the vast majority of quakes occur within 70 kilometers of the surface, some ghostly tremors originate from astonishing depths of 300 kilometers or more, where pressures are crushing and temperatures could melt steel. These deep earthquakes defy everything we thought we knew about how the planet moves, because at such extremes, rock shouldn't fracture, it should flow like warm wax. The mystery begins with the physics of depth. In the upper crust, earthquakes happen when stress overcomes friction along a fault, causing a sudden snap. But below 70 kilometers, the rules change. Intense heat and pressure make rock more ductile, capable of bending slowly rather than breaking sharply. Yet occasionally, the Earth still shakes violently at these depths. The most famous example struck Bolivia in 1994, a magnitude 8.2 quake originating 630 kilometers underground, strong enough to sway buildings in Toronto and Seattle despite erupting from nearly the distance of New York to Chicago straight down. Scientists call these anomalies deep focus earthquakes, and their existence forces us to rethink how faults operate. One leading theory involves mineral transformations. At extreme depths, the atomic structure of rocks can abruptly change under pressure, like graphite squeezing into diamond. These phase transitions might create temporary weaknesses in the rock, allowing sudden slips. Another possibility hinges on trapped water. Even trace amounts dissolved in minerals could lubricate faults when released by the crushing depths. Then there's the thermal runaway hypothesis, suggesting that as rock starts to deform, friction generates heat, which softens the rock further, creating a feedback loop that culminates in a violent rupture. Ghost faults add another layer of intrigue. While most deep quakes cluster near subduction zones where one tectonic plate dives beneath another, some strike in places that defy easy explanation. In 2013, a magnitude 7.5 quake rattled the Sea of Okhotsk, originating 609 kilometers down in what should have been stable mantle rock. Even more perplexing are the deep tremors beneath continental interiors, like those occasionally detected under the Alps or the American Great Plains. These events suggest that deep faults might form through mechanisms we've yet to imagine, perhaps tapping into stresses transmitted across entire tectonic plates. The deeper we probe, the stranger these quakes behave. Unlike their shallow counterparts, deep quakes often produce sharp, distinct seismic waves with fewer aftershocks, as if the fault snaps cleanly rather than grinding. Some even generate unusual ringing frequencies, like a bell struck at the bottom of the world. Researchers have also noticed that deep quakes tend to cluster at specific depth ranges around 300, 500, and 700 kilometers, hinting at invisible boundaries where the Earth's interior chemistry or structure changes dramatically. What makes deep ghost faults so scientifically valuable is their ability to illuminate the unseen. Seismic waves from these quakes act like floodlights, revealing details about the mantle's composition as they pass through. They've helped map colossal slabs of subducted oceanic plates that sink far deeper than once thought, some lingering near the core mantle boundary for hundreds of millions of years. Other deep tremors have exposed mysterious, ultra-low velocity zones, pockets near the Earth's core where seismic waves slow abruptly, possibly indicating molten rock or chemically distinct material. Yet for all their scientific promise, deep ghost faults remain profoundly unsettling. Their very existence proves that the Earth can fracture in places we once considered immune to quakes, under conditions we're still struggling to recreate in labs. If stress can accumulate and release violently hundreds of kilometers down, then our traditional seismic hazard maps focused on surface faults might be missing a hidden dimension of risk. After all, the energy from deep quakes doesn't just vanish, it radiates outward, potentially influencing shallower faults we can't yet predict. The deeper we look, the clearer it becomes. The Earth's interior is far more dynamic and far less understood than our textbooks suggest. These phantom tremors from the abyss aren't just geological oddities. They're urgent reminders that the planet's hidden machinery operates on scales and principles we've only begun to decipher. And with every unexplained deep quake, the Earth whispers a challenge. How well do you really know the ground beneath your feet? One of the most terrifying side effects of ghost fault earthquakes isn't the shaking itself. It's what happens to the ground beneath your feet when the tremors stop. In certain soils, the violent vibrations can transform solid earth into something resembling quicksand, a nightmare scenario called liquefaction. Picture this: a quiet neighborhood street suddenly heaving like ocean waves, then collapsing inward as buried water surges upward, turning sidewalks into sinkholes and foundations into floating rafts. This isn't science fiction, it's exactly what unfolded during the 2011 Christchurch earthquake in New Zealand, where hidden faults triggered shaking so intense that entire suburbs sank into a soupy mess. Liquefaction occurs when water-saturated loose soil like sand or silt loses its strength under seismic stress. Normally, grains of sand interlock like microscopic puzzle pieces, creating stable ground. But during an earthquake, the shaking causes those grains to separate temporarily, suspended in the water between them. The result, solid ground behaves like a liquid, unable to support weight. Buildings tilt drunkenly as their foundations sink unevenly. Underground pipes and fuel lines snap like twigs, creating geysers of water and gas. Roads buckle into grotesque waves, while cars and trees drift like debris on a muddy tide. Christchurch became a tragic case study in this phenomenon. The city's eastern districts, built atop ancient river deposits and reclaimed wetlands, suffered disproportionately when a previously unknown fault ruptured beneath them. Security cameras captured surreal footage of asphalt streets rippling like ribbons before splitting open to swallow parked cars. In the worst-hit areas, the ground slumped by over a meter, leaving houses partially submerged in their own liquefied yards. The quake's shallow depth, just 5 kilometers combined with the region's waterlogged soils, created a perfect storm for destruction. But New Zealand isn't alone in this risk. Geologists now recognize liquefaction zones worldwide, often in places we've aggressively developed without realizing the danger. Much of San Francisco's Marina District, built on debris from the 1906 earthquake, liquefied during the 1989 Loma Prieta quake, causing multi-story buildings to collapse onto their own garages. Tokyo's artificial islands, including the glittering skyscrapers of Odaiba, sit atop loose fill that could turn fluid during the next big tremor. Even more alarming are cities like Jakarta and Mexico City, where centuries of groundwater extraction have caused the ground to compact, making overlying soils even more prone to liquefaction when shaking begins. The science behind this phenomenon reveals why ghost faults pose such a unique threat. Unlike quakes along major plate boundaries, where building codes account for liquefaction risk, ghost fault tremors often strike areas with no seismic preparedness. When the 2001 Nisqually earthquake hit Washington state, the soft soils of Seattle's Pioneer Square, a historic district built on tidal flats, experienced violent liquefaction, damaging century-old brick buildings. Yet just miles away, structures on bedrock barely swayed. This patchwork vulnerability is a hallmark of ghost fault events, where localized geology determines destruction more than distance from the epicenter. Modern engineering offers some hope against this invisible menace. In Japan, builders counteract liquefaction by mixing cement into vulnerable soils before construction, creating a grid of sturdy columns beneath foundations. California's new bayfront developments use massive stone columns called vibrocompaction to densify loose sediments, but the most effective tool might be awareness. Cities like Christchurch now publish detailed liquefaction maps, helping residents understand their risk before the ground turns treacherous. The unsettling truth is that liquefaction doesn't discriminate between ancient faults and newly discovered ones. Wherever loose, wet soils meet sudden shaking, the Earth can betray us in ways that feel almost supernatural. As we continue uncovering ghost faults beneath our cities, the lessons from Christchurch and beyond serve as a stark reminder. The ground's stability is an illusion that can dissolve in seconds, swallowing not just buildings, but our assumptions about where danger truly lies. Predicting the unpredictable. While we can't yet predict ghost fault quakes with precision, early warning systems and public education can save lives. Countries like Japan and Mexico have pioneered alert systems that buy precious seconds before shaking begins. Seconds matter when the Earth starts moving. In Mexico City, a piercing alarm blares through streets and smartphones moments before the ground begins to tremble. This isn't magic, it's physics. Earthquake early warning systems detect the fast-moving but harmless P waves that precede the destructive S waves, giving people critical time to brace, hospitals to pause surgeries, and trains to slow down. During the 2017 Puebla quake, these alerts reached residents a full minute before the worst shaking hit, proving that even imperfect prediction can mean the difference between life and death. Japan's system takes this further, integrating thousands of seismic sensors with automated responses. Bullet trains automatically brake, factory assembly lines shut down, and elevators open at the nearest floor, all triggered by algorithms that analyze tremors faster than human reaction times. The system isn't flawless. False alarms happen, and nearby epicenters offer little warning. But when a magnitude 9 quake struck in 2011, Sendai residents received 80 seconds of notice before tsunami waves arrived. That's 80 seconds to reach higher ground, 80 seconds to grab a child, 80 seconds to survive. What makes these systems revolutionary isn't just their technology, but their recognition of a fundamental truth. We don't need to predict quakes days in advance to mitigate disaster. Even 10 seconds of warning allows gas valves to close, preventing fires that often claim more lives than the shaking itself. In California, the Shake Alert system now delivers notifications via smartphones and public address systems, though its effectiveness hinges on public awareness. A warning only saves lives if people know to drop, cover, and hold on. Habits drilled into Japanese schoolchildren through monthly earthquake drills, but less familiar in regions unaccustomed to frequent tremors. The challenge with ghost faults lies in their unpredictability. Traditional warning systems rely on dense sensor networks along known fault lines, but hidden fractures may rupture without nearby monitoring. Researchers are tackling this by thinking differently, using fiber optic cables as makeshift seismic arrays, harnessing smartphone accelerometers to create crowdsourced warning networks, and even studying unusual animal behavior that sometimes precedes quakes. In one experiment, motion sensors in Italian dairy farms detected cows acting strangely hours before a tremor, hinting at subtle precursors we're only beginning to understand. Public education remains the most universal safeguard. In Nepal, where many ghost faults lace the Himalayas, NGOs teach villagers to recognize natural warnings, like sudden changes in well water levels, while reinforcing homes with simple, earthquake-resistant techniques. Chile's strict building codes, forged through brutal experience with unexpected quakes, now mandate structures that can sway without collapsing, even when the fault responsible wasn't on any map. These solutions acknowledge a hard reality. The Earth will move where it pleases, but preparedness can rewrite the aftermath. The ultimate goal isn't just faster alerts, it's smarter resilience. Engineers in seismically active regions now design buildings with rocking frames that recenter after shaking, while architects experiment with shape memory alloys that allow structures to flex and heal like bones. Urban planners map liquefaction zones with the same urgency as floodplains, and hospitals increasingly locate emergency generators on rooftops instead of basements. Each innovation stems from the same humbling lesson ghost faults teach us again and again. The ground's secrets run deeper than our knowledge, but human ingenuity runs deeper still. While we may never predict ghost fault quakes with the precision of weather forecasts, we're learning to listen to the Earth's whispers before it shouts. Every second of warning, every reinforced building, every drilled response chips away at the chaos these hidden fractures unleash. The Earth's unpredictability is a constant, but so is our capacity to adapt, prepare, and endure. Hollywood loves a good earthquake, the collapsing skyscrapers, the screaming crowds, the heroic last-minute rescues. But when disaster movies turn their attention to ghost faults, they often miss the real horror lurking beneath the spectacle. Take the 2015 film San Andreas, where Dwayne Johnson's character races to save his family from a massive quake along the titular fault. The movie nails the visceral terror of seismic destruction, but real ghost faults don't play by the same dramatic rules. They strike without preamble, in places no disaster planner would think to monitor, turning everyday locations into ground zero without a single foreshock. Science fiction often gets closer to the unsettling truth. In N.K. Jemisin's award-winning Broken Earth trilogy, the planet itself is a sentient, hostile force, its crust fracturing unpredictably in response to human activity. This metaphor captures a chilling reality. Ghost faults frequently react to stresses we impose, whether through fracking, reservoir construction, or even the sheer weight of urban sprawl. The novel's fifth season, earthquakes mirror real-world events like the 2008 Sichuan quake, where a dam's reservoir may have triggered a hidden fault, claiming nearly 90,000 lives. Fiction becomes prophecy when we ignore the Earth's invisible fractures. Even video games are exploring these geological mysteries. Fault Line, an indie survival game, tasks players with navigating a city where the ground shifts unpredictably. No fault lines on the map, just sudden, devastating tremors. The game's most haunting detail, seismic sensors give only seconds of warning, mimicking the real-world challenge of monitoring hidden fractures. Meanwhile, the augmented reality game Quake Catcher turns players into citizen scientists, using smartphone accelerometers to detect actual tremors. A clever blend of entertainment and crowdsourced research that highlights how little we still know about ghost fault behavior. The most insightful portrayals come from unexpected sources. Japanese anime like Tokyo Magnitude 8.0 meticulously depict liquefaction and infrastructure collapse phenomena, rarely shown in Western media but critical to understanding ghost fault risks. An episode might spend minutes showing a character crawling through a tilted, half-sunken office building, capturing the slow-motion nightmare of soil turning to slurry beneath a city. These stories resonate because they focus not on spectacle but on the human aftermath, the shattered routines, the improvised shelters, the quiet despair of losing what you thought was solid ground. What pop culture often misses is the creeping dread of discovery, the moment scientists realize a city sits atop a sleeping threat. This real-life drama unfolded in Seattle, where researchers spent years debating whether the Seattle fault posed a danger before evidence of a magnitude 7 quake 2,000 years ago emerged from marsh sediments. That slow unraveling of geological secrets is less cinematic than a skyscraper's collapse, but far more instructive. It reminds us that ghost faults don't announce themselves with Hollywood fanfare. They're uncovered through painstaking science, one sediment core or LiDAR scan at a time. The takeaway isn't that these portrayals are wrong, it's that reality is stranger and scarier. Ghost faults don't need embellishment to be terrifying. Their true horror lies in their invisibility, their patience, and their refusal to follow our maps. When a fault no one knew existed shakes a region no one thought vulnerable, the aftermath feels less like a disaster movie and more like a cosmic betrayal. The ground itself revealing it was never as solid as we trusted it to be. Perhaps that's why storytellers keep returning to these themes, not to sensationalize, but to grapple with the humbling truth that our planet's secrets run deeper than our understanding. The Sichuan earthquake of 2008 stands as one of the most devastating reminders of why ghost faults terrify seismologists. Striking with a magnitude of 7.9 in what was considered a relatively stable region, it reduced entire towns to rubble in seconds, killing nearly 90,000 people and leaving millions homeless. What made this tragedy even more gut-wrenching was the revelation that the quake originated from a fault no one had mapped, a hidden fracture beneath the Longmen Shan Mountains that hadn't ruptured in recorded history. Schools collapsed, hospitals crumbled, and entire families vanished under concrete because buildings here weren't designed to withstand such violence. The Earth moved where no one expected it to, and the human toll was catastrophic. This pattern repeats wherever ghost faults lurk. Unlike cities along the San Andreas or Japan's Nankai Trough where strict seismic codes mandate reinforced structures and regular drills, regions unaware of their hidden faults often build with fatal complacency. In Nepal's 2015 earthquake, centuries-old temples collapsed alongside modern apartments, their brittle bricks and unbraced concrete no match for a previously overlooked fault beneath the Himalayas. The difference in survival rates between a modern Tokyo high-rise and a Kathmandu apartment isn't just engineering, it's the cruel luck of whether your city knew it sat on dangerous ground. The aftermath of these disasters exposes another harsh reality. Recovery is uneven. Wealthy nations bounce back faster, while poorer communities grapple with the echoes of tragedy for decades. After the 2003 Bam earthquake in Iran, which killed 26,000 along an unmapped fault, survivors endured years in makeshift shelters while reconstruction lagged. Contrast that with California's Northridge quake the same year, where robust insurance systems and federal aid accelerated rebuilding. Ghost faults don't discriminate in their shaking, but human systems amplify their unequal impact. Perhaps the most insidious danger lies in what we don't know. Before the Sichuan quake, the region's most recent major tremor had been 400 years earlier, long enough for collective memory to fade. Oral histories from indigenous Sichuanese communities warned of the mountains walking, but these tales were dismissed as folklore until the ground proved them right. Today, seismologists scour similar stories worldwide, from Native American accounts of the Pacific Northwest's Thunderbird battles to Aboriginal Australian myths about the Earth cracking open. These aren't just stories, they are survival guides from cultures that remembered what modern planners forgot. The lesson from Sichuan and other ghost fault disasters isn't just about better geology, it's about humility. As we keep uncovering hidden fractures beneath Lagos, Istanbul, and Los Angeles, the most urgent question isn't whether the ground will move, but whether we'll heed the warnings before it does. Because when the Earth betrays our trust, the cost is measured not in magnitudes but in lives. The idea that human activity could wake sleeping faults sounds like science fiction, but the science behind it is startlingly concrete. As glaciers retreat and ice sheets melt at unprecedented rates, they're not just raising sea levels, they're altering the very balance of the planet's crust. Picture a giant trampoline slowly releasing tension as weights are removed from its surface. That's essentially what's happening across places like Greenland and Alaska, where billions of tons of ice loss allow the Earth to rebound upward, potentially stirring ancient fractures beneath. In Iceland, where glaciers have shrunk by over 15% in the last century, seismometers now detect swarms of small quakes in regions that were seismically silent for generations. This phenomenon, called glacial isostatic adjustment, isn't just about the ground rising, it's about stress redistribution on a continental scale. When the weight of ice vanishes, pent-up energy transfers horizontally through the crust like a ripple in a carpet, searching for weak points. Studies in Scandinavia show that post-ice age rebound continues to trigger quakes along prehistoric faults, some strong enough to damage buildings. The troubling question isn't whether this happens, but whether modern climate change is accelerating the process beyond natural rates. Water adds another layer of complexity. As melted ice flows into oceans, the added weight reshapes seafloor plates, while emptying reservoirs on land create opposite stresses. The 2008 Sichuan earthquake tragically illustrated this interplay. Some scientists argue the Zippingpu Dam's reservoir, filled just months prior, could have added enough pressure to nudge a hidden fault past its breaking point. Similarly, California's Oroville Dam area experienced a surge in seismic activity after water levels fluctuated dramatically during recent droughts. The mechanics are debated, but the pattern is clear. When we redistribute Earth's water at scale, the ground takes notice. The most controversial aspect isn't the physics, it's the timeline. Traditional geology moves at a pace measured in millennia, but human-driven climate change operates on decadal scales. Are we effectively fast-tracking processes that normally take thousands of years? Paleoseismic records from Canada's Yukon Territory suggest some faults that rupture every 20,000 years like clockwork unless external forces intervene. With Arctic temperatures rising 3 times faster than the global average, we may be conducting an unplanned experiment in seismic triggering. Critics rightly point out gaps in the data. Correlation doesn't always equal causation, and Earth's crust has its own rhythms. But the mounting evidence compels even skeptics to reconsider. In Antarctica, where ice loss is most dramatic, GPS stations detect the bedrock rising 10 centimeters per year in places, a geological sprint that could reawaken rift systems dormant since the Pleistocene. Meanwhile, alpine regions from the Himalayas to the Andes report increased rockfall and microseismicity as permafrost thaws and glacier support vanishes. The implications force us to confront a new dimension of climate risk. Not only might coastal cities face rising seas, but inland areas could grapple with unexpected seismic hazards as ghost faults stir under changing pressures. Cities like Oslo and Vancouver, built on ancient glacial landscapes, now fund research into whether their stable reputations still hold. As one geologist put it, we're not just changing the atmosphere, we're poking the sleeping bear of planetary geology. Whether that bear will roll over or roar remains one of the most urgent and unsettling questions in modern Earth science. The ocean floor holds secrets even more elusive than those beneath our cities, vast, hidden fractures where the seafloor itself can split without warning. While satellite maps make Earth's surface seem fully charted, the reality is starkly different. Less than 20% of the seabed has been mapped with resolution high enough to detect potential ghost faults. This ignorance came at a catastrophic cost in 2004, when a rupture along the previously overlooked Sunda megathrust triggered the Indian Ocean tsunami. The earthquake itself was colossal, a magnitude 9.1, but the true horror lay in how little anyone knew about the fault that caused it. Whole coastal communities had minutes to react as waves up to 30 meters tall erased shorelines across 14 countries, claiming over 230,000 lives. What makes submarine ghost faults uniquely dangerous is their ability to displace enormous volumes of water when they slip. Unlike land-based quakes that shake buildings, undersea ruptures can unleash energy both upward and outward, creating tsunamis that amplify as they race toward shore. The 2011 Tohoku earthquake off Japan's coast demonstrated this terrifying duality. The seafloor near the fault dropped by 7 meters in places while other sections thrust upward 9 meters, displacing enough water to generate waves that overtopped 40-meter seawalls. Even more unsettling, the fault's full extent wasn't recognized until after it ruptured, despite Japan having the world's most advanced monitoring systems. The challenges of studying these submerged threats are as vast as the oceans themselves. While land faults leave scars visible in road offsets or mountain ranges, submarine fractures often hide beneath kilometers of water and layers of sediment. Traditional ship-based sonar mapping is painstakingly slow. Covering an area the size of Manhattan can take weeks. New technologies are changing the game, though. Autonomous underwater vehicles equipped with multi-beam sonar now prowl the depths, revealing features like the Cascadia subduction zones, silent slips, where the seafloor creeps without major quakes, a behavior that might precede catastrophic failure. Even more promising are fiber optic cables repurposed as seismic antennas, detecting faint tremors through subtle changes in laser light traveling through the glass strands. Some of the most alarming discoveries come from areas once considered seismically dormant. The Caribbean's Muertos Trough, for instance, was assumed to be inactive until researchers found evidence of a massive landslide triggered by a prehistoric quake. Similarly, the Mediterranean's Hellenic arc has unleashed tsunamis throughout history from faults that evade traditional detection. Perhaps most sobering is the realization that major population centers, from Lisbon to Los Angeles, sit vulnerable to offshore faults we've yet to identify. The 2005 Kashmir earthquake proved how inland faults can devastate mountainous regions, but an unseen rupture beneath the Atlantic or Pacific could threaten millions living along coastlines. The silver lining lies in how far detection methods have advanced since 2004. Today's ocean-bottom seismometers form underwater networks that pick up tremors too faint for land-based stations. Satellite altimetry can now detect sea surface height changes as small as a few centimeters, clues to underwater deformation. And machine learning algorithms scour decades of seismic data for patterns that might predict where the next hidden fault lurks. Yet for all this progress, the oceans remain the planet's last great frontier for earthquake science, their depths hiding fractures that could rewrite our understanding of seismic risk. When the seafloor moves, it doesn't just shake the Earth, it moves entire oceans, and in that movement lies a humbling truth. We've mapped the surfaces of Mars and Venus in greater detail than our own planet's seabed. Until that changes, ghost faults beneath the waves will keep their secrets and their potential for sudden, devastating betrayal. When the ground moves unpredictably, our buildings must learn to dance. That's the philosophy behind today's most cutting-edge earthquake engineering, where the goal isn't just to resist tremors, but to move with them. In Tokyo, the towering Mori building sways like a metronome during quakes, its foundation resting on hundreds of rubber and steel isolators that absorb and redistribute energy. These base isolators act like shock absorbers for entire skyscrapers, decoupling the structure from the shaking ground below. During the 2011 Tohoku earthquake, buildings equipped with this technology swung gently while rigid structures crumbled, proving that flexibility can outlast brute strength. The real innovation lies in materials that bend without breaking. Shape memory alloys metals that return to their original form after deformation now reinforce critical joints in bridges and hospitals from Chile to California. In Christchurch, where liquefaction swallowed entire neighborhoods, engineers are testing foundations filled with recycled rubber tires that compress during shaking, preventing sudden settlement. Even ancient techniques are getting a high-tech revival. Japanese pagodas, which have survived earthquakes for centuries thanks to their interlocking wooden frames, inspire modern timber high-rises with similar flexible joints. For ghost fault zones where the direction of shaking can't be predicted, engineers deploy omnidirectional defenses. The San Francisco International Airport's control tower stands on a network of ball bearings that allow it to slide in any direction, while Taipei 101's massive tuned mass damper, a 660-ton steel pendulum suspended near its peak, counters swaying motions with precise, physics-driven resistance. These aren't just engineering marvels, they're acknowledgments that we can't always anticipate the Earth's movements, but we can design structures that adapt in real time. The most revolutionary approaches rethink construction from the ground up. Self-healing concrete, embedded with bacteria that secrete limestone to repair cracks, could prevent the cumulative damage that dooms many buildings after multiple quakes. In Italy, researchers are testing invisibility cloaks for structures concentric rings of plastic and metal buried around foundations that deflect seismic waves like armor. Even more radical are floating foundations being piloted in Jakarta, where buildings essentially hover on layers of pressurized water during tremors, isolating them from ground motion entirely. What unites these solutions is a paradigm shift from resistance to resilience. Older seismic codes focused on preventing collapse, a standard that still leaves buildings unusable after major quakes. The new gold standard, called functional recovery, ensures hospitals keep operating and apartments remain habitable even after violent shaking. When the next ghost fault ruptures beneath an unprepared city, these innovations could mean the difference between a disaster and a survivable event. The Earth's hidden fractures will keep challenging us, but human ingenuity is rising to meet them. One flexible beam, one rolling foundation, one self-healing wall at a time. Mapping the Earth's hidden fractures in 3 dimensions isn't just a scientific ambition, it's a race against time. Projects like EarthScope are revolutionizing our understanding by turning the entire North American continent into a living laboratory. Imagine a network of hundreds of seismic sensors, GPS stations, and magnetotelluric probes stretching from Alaska to Mexico, all feeding real-time data into supercomputers that assemble the most detailed picture of the crust ever created. This isn't theoretical. EarthScope's transportable array has already uncovered subtle deformations in regions once considered geologically inert, hinting at stresses building along ghost faults we can't yet see. The next leap forward lies in combining these terrestrial observations with space-based eyes. NASA's upcoming NISAR satellite, set to launch in 2024, will use advanced radar to measure ground movements down to the millimeter across the entire planet every 12 days. Paired with machine learning algorithms, this torrent of data could reveal patterns in crustal strain that precede major quakes, like silent alarms ringing deep below our feet. Already, pilot programs in California have demonstrated that AI can spot anomalous seismic signals months before rupture, patterns too subtle for human analysts to detect. But the real game changer might be quantum sensing. Researchers at Berkeley are developing gravimeters so sensitive they can detect density variations caused by stress accumulation along buried faults. These devices, which exploit the quantum properties of falling atoms, could one day form networks dense enough to track stress migration in real time, like weather radars for the solid Earth. Early tests in the Pacific Northwest have successfully identified slow slip events, those silent, days-long fault movements that might telegraph bigger quakes to come. The ultimate goal, a planetary-scale nervous system where every tremor, no matter how faint, contributes to a predictive model. Europe's EPOS project is stitching together decades of seismic data into a unified digital framework, while Japan's DONET system blankets the seafloor with sensors along the Nankai Trough. These efforts share a common vision, transforming earthquake science from reactive to anticipatory. Instead of studying faults after they rupture, we'd monitor their vital signs continuously: stress levels, fluid pressures, microfracturing, like doctors running diagnostics on a patient. Yet for all this technological promise, the biggest hurdle remains human. Ghost faults don't respect political borders, and neither does seismic risk. The Mediterranean's complex fault systems, for instance, span 20 countries with vastly different monitoring capabilities. Bridging these gaps requires unprecedented international collaboration, something the Global Earthquake Model Foundation is pioneering by standardizing risk assessments worldwide. Their open-source platform allows scientists from Portugal to Pakistan to share data and modeling tools, creating a mosaic of regional insights into a global picture. The future of ghost fault research isn't just about better instruments, it's about rewiring how we think about geological risk. As machine learning uncovers correlations between groundwater levels, magnetic field fluctuations, and seismic activity, we're learning that the Earth speaks in a language far more nuanced than simple cause and effect. What emerges is a humbling realization. Our planet's crust is a dynamic, interconnected web where a stress shift in Wyoming might influence a fault in Missouri, where melting glaciers in Alaska could tweak tectonic tensions in Chile. This isn't science fiction. It's the frontier of geoscience today, a world where fiber optic cables double as seismic antennas, where satellite constellations track continental breathing, where quantum physics meets ancient geology. With every hidden fault we map, every stress transfer we model, we're peeling back another layer of the Earth's secrets. And somewhere in that growing pool of data might lie the keys to turning ghost faults from mysterious threats into manageable risks, before the ground reminds us once again how little we truly control. When the ground shakes without warning, preparation becomes the thin line between chaos and survival. Unlike regions along major fault lines where earthquake drills are routine, areas near ghost faults often lack that ingrained awareness until the unthinkable happens. Take the case of Mineral, Virginia, where residents had never practiced drop, cover, and hold on before the 2011 quake sent bookshelves toppling and chimneys crumbling. Those who instinctively knew to shelter under sturdy tables fared better than those who ran for doorways, proving that even basic knowledge can rewrite outcomes when the Earth betrays expectations. Securing your space doesn't require seismic engineering, just foresight. Heavy furniture like bookshelves and televisions become deadly projectiles during shaking, but a few strategic straps or brackets can anchor them to wall studs in minutes. Water heaters, often overlooked, should be strapped to prevent ruptured gas lines, a leading cause of post-quake fires. Even simple measures like keeping hallway paths clear and storing breakables low can prevent injuries when seconds count. After the 2018 Anchorage earthquake, survivors credited these small precautions with saving them from worse harm as their homes convulsed around them. Community-wide readiness transforms individual actions into collective resilience. In Japan's Tohoku region, where tsunamis follow quakes, color-coded evacuation routes painted on sidewalks guide panicked residents to high ground. Chilean towns conduct annual Dia de la Seismology drills, simulating everything from building collapses to bridge failures. These exercises aren't just about muscle memory. They reveal gaps in planning, like the Seattle School District discovering their earthquake kits lacked pediatric medications after a surprise drill. When ghost faults rupture, familiar landmarks can vanish under dust or debris, making pre-identified meeting points and out-of-area contacts essential for reuniting separated families. Technology now puts preparedness in everyone's pocket. Apps like my Shake Harness smartphone accelerometers to detect tremors, delivering personalized alerts faster than traditional systems. Earthquake early warning networks, once limited to nations like Japan and Mexico, now cover parts of the US and Europe, offering precious seconds to shut off gas lines or brace for impact. Social media's role can't be overstated either. During the 2019 Ridgecrest quakes, community Facebook groups became lifelines, sharing real-time damage reports and supply needs faster than official channels. Yet the most potent tool remains education tailored to ghost faults' unique threats. Unlike boundary faults where aftershocks follow predictable patterns, hidden fractures can trigger scattered, prolonged shaking. Residents in New Madrid's seismic zone learn to watch for sand boils and fissures, signs of liquefaction that traditional quake guides omit. Schools in Charleston, South Carolina, teach students to identify earthquake weather myths while emphasizing the real danger of brick facades in historic downtowns. This hyperlocal knowledge bridges the gap between abstract risk and tangible action. The unsettling truth is that ghost faults ensure nowhere is truly zero risk. But from Tokyo to Tennessee, communities are proving that preparedness isn't about predicting the unpredictable. It's about building adaptable systems that hold fast when the ground does not. Whether through neighborhood response teams stocking makeshift medical kits or engineers retrofitting century-old buildings with hidden reinforcements, each layer of readiness chips away at the chaos these hidden fractures unleash. Because when the Earth moves in ways we can't anticipate, the best defense isn't fear, it's practiced, pragmatic resilience. Ever noticed how some people swear they can predict earthquakes by watching their dog's behavior or feeling a sudden shift in humidity? These persistent myths, often passed down through generations, create dangerous misconceptions about how earthquakes actually work. Take earthquake weather, the belief that certain atmospheric conditions precede tremors. Ancient Greek philosophers wrote about hot, still air as a warning sign, while in modern California, some still point to unusual cloud formations as harbingers of the big one. Yet decades of seismic data show no correlation between weather patterns and fault activity. Quakes strike just as often in rainstorms as under clear skies, at midnight or noon. The myth persists because humans crave patterns, instinctively linking unrelated events when faced with the terrifying randomness of the ground's movements. Animal predictions fall into a similar trap, from rats fleeing buildings in ancient China to captive elephants acting restless before the 2004 Indian Ocean tsunami. Anecdotes abound. While animals might detect subtle seismic waves seconds before humans, thanks to heightened sensitivity to vibrations or electromagnetic changes, there's zero evidence they can predict quakes days or weeks in advance. The U.S. Geological Survey's famous Parkfield experiment monitored farm animals for years alongside seismic sensors, finding no reliable pre-quake behavior. The reality: animals react to countless stimuli daily. When a quake follows, we remember the coincidence while ignoring all the false alarms. Then there's the opening gap myth, the Hollywood image of chasms splitting the earth during tremors. While surface ruptures do occur along known faults like the San Andreas, most ghost fault quakes cause horizontal shaking or subsidence rather than canyon-like cracks. The misconception stems from rare liquefaction events where water-saturated soil temporarily loses cohesion, creating fissures that close again post-quake. During the 2011 Christchurch disaster, some falsely reported new fault lines opening what they actually saw were pre-existing drainage cracks widened by soil movement, not gaping voids ready to swallow cars. Perhaps the most dangerous myth is that small quakes release pressure and prevent larger ones. While it's true that some fault systems exhibit predictable stress release, ghost faults operate differently. Their sporadic, unpredictable nature means a cluster of minor tremors could signal growing instability rather than safety. The 2009 L'Aquila earthquake in Italy tragically demonstrated this. After months of small tremors, officials downplayed risks, claiming the shocks were relieving strain. When a magnitude 6.3 quake struck, killing over 300, it exposed the flaw in assuming all faults follow the same rules. Debunking these myths isn't just academic, it saves lives. Communities that understand quakes can strike without warning signs are more likely to prepare year-round. Schools in ghost fault zones now teach kids to ignore folk wisdom and instead practice drop, cover, and hold on drills monthly. Emergency kits shift from folklore-based items like lucky charms to practical supplies, water, medications, and battery-powered radios. Scientists combat misinformation with tools like the "Did you feel it?" citizen reporting system, which crowdsources real-time shaking data to separate fact from fear after tremors. The deeper lesson here is about respecting uncertainty. Ghost faults remind us that the Earth doesn't follow human narratives or convenient patterns. While we've replaced ancient tales of angry gods with modern myths of animal oracles, the core truth remains: the ground moves on its own terms. Preparing for that reality, not the stories we tell about it, is what ultimately keeps us safe when the unseen fractures beneath us finally stir. Ghost faults don't respect borders. They hide beneath continents and oceans, indifferent to the political boundaries we've drawn above them. That's why cracking their code demands something rare in science: true global teamwork. Picture seismologists in Japan analyzing data from a tremor in Chile, while researchers in Norway compare notes with colleagues in New Zealand about similar hidden fractures under their fjords. This isn't just cooperation, it's a planetary detective squad piecing together clues from every corner of the Earth. The backbone of this effort is organizations like the Global Earthquake Model Foundation, which pools data from over 100 countries into open-source risk maps. These aren't your typical atlases. They layer historical quake records with real-time GPS measurements, satellite radar scans, and even crowd-sourced shaking reports after tremors. When a mysterious quake rattled eastern Australia in 2018, this shared database helped trace it to a buried fault no single nation's instruments could have identified alone. The revelation: stress from the distant Pacific Plate was transmitting hundreds of kilometers inland, finding weak spots that local surveys had missed. UNESCO International Platform for Reducing Earthquake Disasters takes collaboration further, turning research into life-saving action. Their workshops train engineers from Nepal to Nicaragua in retrofitting schools for ghost fault shocks, while anthropologists document indigenous seismic knowledge that often predates modern geology. In the Himalayas, Sherpa guides ancestral stories about angry mountains now inform hazard maps alongside satellite data, a fusion of ancient wisdom and cutting-edge tech that's rewriting preparedness plans. Technology has dissolved the barriers like never before. The European Plate Observing System streams live data from seismic stations across 40 countries, allowing algorithms to spot strain patterns that might precede major quakes. When Turkey's East Anatolian Fault stirred in 2023, Romanian sensors detected subtle crustal deformations days before the devastating Kahramanmaraş earthquakes, a hint that real-time warning networks could someday span continents. Even amateur scientists contribute through apps like Raspberry Shake, turning home seismometers into a crowdsourced monitoring web sensitive enough to catch tremors from buried faults too small for official networks. But the real test comes when disaster strikes. After the 2021 Haiti earthquake, which ruptured a previously unmapped fault, teams from 18 nations deployed temporary seismic stations within days. Their shared data revealed aftershocks migrating toward Port-au-Prince, warning of potential further damage. Meanwhile, Mexican engineers shared blueprints for earthquake-resistant adobe homes, adapted from designs that survived their own ghost fault quakes. These aren't just academic exchanges, they're lifelines thrown across oceans when the ground betrays us. The stakes of this cooperation couldn't be higher. Cities like Istanbul and Tehran sit atop cryptic fault networks that could unleash catastrophes transcending borders. A major quake in the Himalayas wouldn't just devastate Nepal, it could send humanitarian crises rippling through India, China, and beyond. That's why initiatives like the Transboundary Seismic Risk Project now treat fault zones as shared responsibilities rather than national secrets. When Iranian researchers shared detailed maps of the Zagros Mountains' hidden fractures with Iraqi counterparts, it wasn't just diplomacy, it was survival logic. Yet challenges remain. Some governments withhold sensitive geological data, fearing economic impacts on tourism or insurance. Others lack resources to monitor their territories comprehensively, leaving blind spots in the global seismic net. The solution: projects like the African Seismic Hazard Model, where international partners fund seismic stations across the continent, with all data openly accessible. It's a model of science without borders, a proof that when the Earth itself refuses to play by our rules, humanity's best defense is unity. What emerges from this worldwide effort isn't just better science, it's a new way of seeing our planet. Ghost faults remind us that the ground beneath our feet is a shared frontier, its secrets too vast for any one nation to unravel alone. But with every byte of shared data, every joint research paper, and every life saved by cross-border warnings, we're weaving a safety net that might one day catch us all when the hidden Earth moves. Ghost faults force us to confront a humbling truth beneath our cities and farmlands. The Earth still writes its own rules in fractures we can't always see. For all our satellites and sensors, the planet keeps secrets in its crust that defy prediction, reminding us that human knowledge has limits nature happily ignores. These hidden fractures aren't just geological curiosities, they're teachers. Every unmapped fault that ruptures without warning, every tremor in a stable region, chips away at our arrogance, replacing it with something more valuable: respect for the forces that shaped this planet long before we walked it. Think of the New Madrid earthquakes 2 centuries ago, bending the Mississippi River backward like a ribbon, proof that even continents have memory. Or the Sichuan quake of 2008, where children perished in schools built over a fault no one knew existed. These tragedies aren't just calls for better engineering, they're invitations to listen more closely to the Earth's whispers. When Native American oral traditions describe mountains walking, or medieval monks chronicle unexplained tremors, they're not just stories, they're data points in a planetary puzzle we're still assembling. The real gift of studying ghost faults isn't just safer buildings or sharper warnings, it's a shift in perspective. Every time we uncover a hidden fracture, we're reminded that the ground beneath us isn't a static stage but a dynamic, evolving system. Those ancient continental collisions, those failed rifts from 500 million years ago, their scars still matter, still influence where stress gathers and releases today. It's geology as time travel, revealing that the Earth operates on timelines far longer than human ambition. So where does that leave us? Not in fear, but in partnership. With every ghost fault mapped, we're rewriting what it means to live on this planet not as conquerors, but as adaptable inhabitants. Cities like Tokyo and San Francisco now build with flexibility, designing skyscrapers that sway rather than shatter. Communities from Chile to Nepal train not just for the quakes they've seen, but for ones their great-grandchildren might face. That's the paradox of these hidden dangers. By acknowledging how much we don't know, we actually become wiser stewards of the landscapes we call home. If there's one lesson ghost faults hammer home, it's that preparedness is a conversation, not a destination. It's scientists collaborating across borders, engineers learning from ancient builders, and ordinary people understanding that the ground's stability is a privilege, not a guarantee. So keep asking questions, stay open to the unexpected, and remember, the next time the Earth moves in a place it shouldn't, it's not an anomaly. It's the planet reminding us who was here first. Thanks for joining this journey into the Earth's hidden fractures. If these mysteries fascinate you as much as they fascinate me, hit that like button, subscribe for more deep dives into our planet's secrets, and drop a comment below sharing where you live. Have you ever felt a quake that defied explanation? Stay curious, stay prepared, and I'll see you in the